All right, thank you for these wonderful talks here. I'm going to be talking at a very different scale of processes here. But this is work that a lot of it I'm going to present to you was actually published by a series of papers by a former PhD student of mine, Andy Hesselbrock. And then there's some stuff that my current grad student, Kasta Badnan, has also been working with. He's got a poster over here, but it's on a completely different topic. So he's a productive dude. That's great. All right, so first of all, what I'm going to be talking about two mechanisms. Most of it is this first one. These are spontaneous ring satellite cycles. In order to make this happen, there's really only 4 ingredients you need. You need to have some sort of tidal disruption that can basically break up a satellite, viscous spreading that causes a ring to form and spread out, and then formation of a new satellite at the Roche limit at the edge, plus some ring satellite interactions via Lindblad torques and other things. And then inward tidal migration. If you have these 4 ingredients, you get these spontaneous cycles of rings and satellites. So I'm going to go through each of these processes one by one to kind of show you the assumptions and what goes into them. The first thing is, in order to get inward tidal migration, the main thing you have to have is you have to have a satellite that's orbiting interior to the synchronous orbital period, or the co-rotation radius. Because if you're on the outside, like our Earth moon is, you'd be migrating outwards instead of inwards. There's this very simplified view of the tidal migration scale, the speed at which you're inwardly migrating. And then if you migrate in close enough, you get into the Roche zone. Now, if you're from a astronomy, stellar gas giant planet perspective, there's only a Roche limit. But when we start talking about satellites and rocky things, actually there is no single defined Roche limit, because these rocky bodies can actually have cohesion, and even just like friction can kind of hold their shape. And so we define something called the rigid Roche limit, which is kind of an approximation of, imagine the tidal stresses across a rigid sphere. So somewhere in this zone, which it's kind of ambiguous where, is where a satellite can persist before it's broken up. And when we actually look at ring systems around planets, and here's 2 representative examples of ring systems, using this the so-called Roche critical density that Matt Tiscarino wrote about, where you kind of invert the Roche problem to look at the density at which the Roche limit occurs. And you can see that basically dense rings, like the main rings of Saturn, are basically inside the Roche limit for these low density materials. Uranus has rings too, but the inferred density is much higher. And then there's these scattering of little satellites really close to the ring edge. All right, if you have dense, optically thick rings where collisions are basically driving a lot of the dynamics, you get what's called viscous effects. Basically, you can model a dense collisional ring like a fluid, and there's a term in that fluid approximation that acts like viscosity. And so this is an example of showing from using a code very similar to Julien Salmon's code, where you start with a very narrow ring around Saturn, and then you allow it to spread in just like a blob of honey or something. It spreads out and goes both inwards and outwards. If you have a satellite and a ring together, you can get what are called the Lindblad resonances and Lindblad torques. So if you basically imagine a satellite here perturbs the ring material, there's this pattern that gets set up if you're in resonance. There is some amount of lag, just like in tides. There's a bit of a lag angle, so there's a slight asymmetry in the mass and accelerations. Now, unlike tides, this always leads to satellites moving away from the ring. So the Lindblad torques always repel satellites away from massive rings, and the rings likewise get pushed inwards. All right, so the Lindblad torques, you can kind of look at, there's lots of great equations if you're into that sort of thing for what they are, but for our purposes, know that the most that you can actually get a satellite to be repelled from a ring is basically where the 2-to-1 resonance occurs. And so I'm going to call that A sub Lind. So that's the Lindblad distance. It's as far away as ring torques can actually push the satellite away. All right, so with these ingredients in mind, we identified 3 regimes of evolution. So you have one where if the synchronous period is inside the Roche limit, then tides and Lindblad torques always move in the same direction, and so you always get satellites moving away from rings. So if you make a satellite near the ring edge, it's always repelled away from it. You have another, we call that the slingshot regime. In this regime, if you put the synchronous orbit far away, tides and Lindblad are always in opposition to each other. So if Lindblad torques are high enough, you can move outwards, but tides will want to bring you back inwards. And you also have this interesting case of an intermediate situation. If your A sub Lind is outside of synchronous, if the ring torques are strong enough, you can actually push it over the edge and you get the slingshot regime. And if it's not massive enough, you can't go far enough and you'll get what's called the boomerang regime. I'm going to show you examples of each one of those and these basically places where we think they're applicable. So the first one, this is Saturn's rings. So this is our own reproduction of a plot that was done in Charnot et al. 2010. These are, what I'm going to show you here, a series of these plots. You're going to see the ring mass density on one axis, that's plotted here. Mass of any satellites, which we'll see as dots, are here. Distance in terms of planetary radii. These are actual observed satellites, the so-called ring moons of Saturn. And what we're going to start with in the model here is we're going to put a mass of ring material in the narrow annulus, and we're going to let it evolve. You see the ring spreads out, and it spits out satellites, and you get this nice sort of trend that seems to match observations of satellites that grow and basically match what we see on the outside here. All right. And this is the slingshot regime. Satellites are always going to move away. Now, we looked at this, the planet Uranus, because it's a more slowly rotating planet than Saturn. It's actually in this intermediate regime where the A Lind is actually on the outside of A sync. And so we actually proposed a scenario if you had a much more massive ring early in Uranus's history, you could have had enough mass to kick out a satellite over that, and it would be about the mass of Miranda. And then every satellite after that would basically cycle in this boomerang regime. And so possibly you could explain the so-called Portia group and these other little satellites as the remnant of this cycle behavior that once occurred. Problem with this is that it's, at least for making Miranda, it's actually really hard for tides to actually pull you from A Lind out to where we see Miranda. I had to go over 10 billion years to even get close. So it may not actually work for Miranda, but it's still, Uranus is theoretically in this regime. Now, what actually motivated us to do a lot of this is actually looking at the Mars system. So in our hypothesis, Mars is actually in a situation where if it had ever had a ring, it's in this boomerang regime. So imagine if early in the solar system history, you create a debris disk, kind of like our moon-forming disk, that's big enough that it initially goes over, parts of it go over the synchronous orbit. You'd create a more massive inner satellite and a ring and some Deimos, and you get through this basically cycle, back and forth, until eventually you get something after about 6, 7, 8 cycles, depending on your parameters, that resembles Phobos. All right, so we've been actually proposing this as a mechanism for creating Phobos and Deimos, and for explaining the evolution of Phobos. Now, there are some issues with this. In our simplified model, we're actually missing a lot of relevant physics. And so we always have a remnant ring each time. And so we're actually working that problem right now. Some of the physics that we're missing that I think are really important is we don't incorporate radiation effects or resonances. Some really promising, saw really promising work at EPSC a few weeks ago that the Yarkovsky shock effect might actually remove this ring between cycles. But that's ongoing work right now that me and Matija Chuk are working on. Now, the other thing that we're working on is a different kind of process that could be thought of as a kind of cycle. It's just not a spontaneous one. This is called the sesquenary catastrophe. This was proposed by my colleague Matija Chuk. The idea is if you have a satellite, small satellite, on an inclined or eccentric orbit, and you hit it with a primary impactor, some portion of that debris that doesn't either escape the system entirely or rain back down as a secondary impactor remains in orbit around the primary. And those are what are called sesquenary impactors. So you get this population of debris that stays in orbit. Now, at first, that debris is not going to be very far from the origin point, so it's going to be aligned like that. But due to differential precession, eventually that becomes misaligned, and that increases the relative velocity between this debris and the material that it came from, or the satellite where it came from. Now, under this, what Mattia proposes that if your excitation value goes above around here, the re-impacting debris is actually will generate more debris than you started with, and so results in this sort of runaway cascade. So Kasabanan has been modeling this. We have a paper that's in review right now where he's showing with a numerical model, an n-body model, that even if you hit once on Deimos, if Deimos's orbit is a little more eccentric or inclined than it currently is, then it'll eventually fragment itself and completely tear itself apart. All right, so I'm going to stop there, and I'm going to show you these fun movies and entertain any questions. So thank you.
Thank you. Jay Farihi, University College London. Please, apologies for my ignorance and naivete, but isn't one or both of Deimos or Phobos in retrograde, and does your model account for that?
No, actually, they're both prograde, both coplanar. They look like regular satellites that are, this is why I don't think that there's any real compelling evidence that they're captured or anything like that.
My mistake, thank you.
Yeah. So I think you might be thinking of the fact that one is interior to the synchronous orbit, so it's migrating inwards towards Mars as Phobos, and Deimos is migrating out. Right.
Thank you. Hello, this is Bryce Bolton speaking from Eureka Scientific. So is there a chance that any of this material during these boomerang processes could have escaped orbit around Mars and be floating around there as Trojans of Mars?
Not in the boomerang regime, because there's just not enough. There's not enough energy or velocity. This is really tidal disruption. It's a very local event. Now, impacts into these could release some amount of material. But, you know, Phobos and Deimos are small. They're like the size of the Trojans themselves, right? They're only a few kilometers across. So more likely, it's either debris from early planetesimal, planet formation, or something kicked off of Mars. But Phobos and Deimos are very tiny little potatoes.